Now we're going to spend some time talking about the Earth's shape and its surface. This is known as geodesy, the study of the Earth's shape and surface. Ancient Greek scholar Erastosthenes showed us that the Earth was spherical, kind of like his head in this image. Modern research, however, shows that the Earth is not a perfect sphere. In fact, the Earth's topography, or surface elevation, ranges from nearly 20 kilometers from the highest point on Earth, Mount Everest, to the Marianas Trench, which is around 11,000 meters below the surface of sea level. Now, sea level is going to be used as a reference for all Earth's surface and seafloor elevations. So everything we do to talk about the surface of the Earth, the variability in the surface of the Earth, is related to sea level, something that we will see later on in the course isn't a steady feature of the Earth. Sea level rises and falls for a wide variety of reasons. Here we have an image of Mount Everest on a somewhat typical climbing day. This is the highest point on the surface of the Earth today. Conversely, in the Pacific Ocean, we have the Challenger Deep, which is located to the west of the island of Guam. This is a negative 11,000 meters, whereas Mount Everest is a positive 8,850 or so meters. Now, you may have seen a few years ago a U.S. congressman talking about Guam, and he was concerned that if we put more people on Guam, that Guam would tip over and fall into the ocean. The question he posed towards the U.S. Admiral was related to this increase in size of population on Guam. The Admiral confirmed that it wasn't really a problem that they were concerned about, the tipping over of islands. Probably about 2 years ago or so, I was giving a lecture on the Marianas Trench, and as I was walking home, I saw on a pole this poster, and they were performing at Louis apparently. I didn't make it. I don't know anything about Down with Webster, but anyway, once COVID-19's cleared up, there's a possibility they'll come back. Okay, so how did Eratosthenes do this thousands of years ago? Well, he used stadia as his unit of distance, and this turns out to be good and bad. It is a widely used unit of distance. His accuracy may have been somewhere between 1% and 16%. The problem is, although stadia is widely used, no one really knows what it was, the actual distance, the length of a stadia. Initially, it's supposed to be 1 second of 1 minute of 1 degree. That's about 40 meters or so. Other numbers that are thrown around are 607 feet to around 630 feet for the length of a stadia. The modern furlong, which is used in horse racing mostly, is close to the historic length of a stadia, about 1/8 of a mile or 660 feet. So these numbers are going to get all jumbled and confused in your head. The thing to remember here, the most important thing, is that he was able to do this fairly accurately. And the way he did it was he positioned the sun at noon relative to this well. So the well is perpendicular to the Earth's surface. And with sunlight perfectly perpendicular to the Earth's surface at noon, it's going to shine straight down to the bottom of this well. Now, if you go 800 kilometers away to Alexandria, one of the major centers of learning at the time, and you look at the orientation of a tall rod that is vertical at that same time over this distance, you get an angle of 7 degrees here between the vertical and the incoming rays of the sun. This is then converted, as you see here, the distance between Alexandria and Syene is going to be calculated here from the 7 degrees of the 360 degrees of the size of the totality of the Earth. So it's fairly simple math that comes to a fairly significant conclusion. The Earth is round. We knew that thousands of years ago, thanks to work from people like him. Now, when we look at Mount Everest as a positive feature, we can see here it's located right around the juncture between India, Nepal, Tibet, and China. Just recently, in fact, this year, or last year, 2020, an agreement was reached by the Chinese and the Nepalese that established its height at 8,849 meters. The depth of the Challenger Deep is still wavering by a few meters here and there, but generally it's accepted to be around 10,929 meters or 11,000 meters. In feet, for those of you that are fans of the old system, Everest is about 29,000 feet high, and the Challenger Deep is about 36,000 feet below sea level. When we investigate the Earth with depth, we notice that the Earth appears to have layers. Seismic waves that travel through the Earth behave in a way that's different depending on the depth. So this change in behavior with depth provides us with some idea, some illumination of what's going on inside the Earth. Compression and shear waves behave differently and are going to be bent or absorbed at layer boundaries within the Earth. So we transition from a solid to a liquid, or a solid to a more dense solid. That's going to change the behavior of these waves. The Earth's interior is therefore layered according to density. The rock density at the surface of the Earth is slightly less than 3.5 grams per centimeter cubed. The whole Earth density is about 5.5 grams per centimeter cubed. Now we can measure rocks at the surface to get an accurate idea of this number. We can use the gravitational pull, some basic physics, to determine this number. And we can use this number with this number to calculate this number, that the core density should be about 8 grams per centimeter cubed to make this relationship work. So much greater, almost 3 times the density of surface rocks, and almost twice the density of the whole Earth. So the core is significantly denser than other portions of the Earth. When we look at it schematically, we can see that we have a crust, an outer rigid portion of the Earth. We have a mantle, which is mostly plastic, kind of toothpastey, very thick, very hot toothpaste. And then we have a liquid iron outer core, a very dense liquid, molten metal. And then we have a solid inner core that's composed principally of iron. The outer core is also composed principally of iron. Now, early on in the Earth's history, as the Earth was getting bashed by planetoids and planetesimals, asteroids, meteors, meteorites, dust, it was pulverized. And this pulverized material was somewhat homogeneous. As this bashing continued, the heating of the Earth continued, and that provided the time and the impetus for differentiation. This differentiation is going to occur gravitationally. So we start out with a bulk Earth with a uniform composition. We begin to develop oceans and atmospheres above the surface of the Earth. These became more prevalent as the Earth cooled. And we begin to see, again, differentiation of the Earth into continental and oceanic crust, depleted mantle, and primitive mantle, with the core remaining relatively isolated. This overturn of materials, the sinking of the iron towards the center, and the migration of the lighter elements towards the surface is known as the iron catastrophe. Catastrophe means to turn over. Doesn't necessarily mean a disaster. We use it as a disaster term, but it really means to turn over. The net result is, if we send seismic waves through the Earth, we're going to see change in velocity. With the P waves, we're going to see an increase in velocity with increasing depth due to density, then a slight decrease right here where there's partial melting of the upper mantle. And then as density increases further into the Earth, the P waves are going to increase in velocity until they reach the liquid iron outer core, where they slow considerably. And then again, they increase in speed as they go further and further into the core, towards the center. S waves behave differently. These are shear waves. They're going to show a similar profile until we get to the liquid iron outer core. At this point, because they're shear waves, they don't propagate through a liquid, they go away. Suddenly they reappear in the inner core, and this is the result of P waves being converted into S waves. So the S waves don't come back, They're just created in a different way at this boundary. When we put these different materials together, the crust is going to be composed of continents made of less dense material. This less dense material literally floats on more dense material. So in this case, we have continental crust comprised of carbonate rock and silicates predominantly. That's going to ride on oceanic crust occasionally. Usually the oceanic crust being weaker and thinner will get pushed underneath the crust or abducted onto the crust. This is all going to float on a mantle, which is much more dense. The abrupt changes in density between the Earth's major interior layers are caused by changes in the chemical composition of those layers and the resulting minerals that are created from that changing chemical composition. The inner core is almost entirely iron with a little bit of nickel, 94% iron, 6% nickel. The outer core, 85% iron, 5% nickel with just a little bit of sulfur and a little bit of oxygen. And this sulfur turns out to be very important in generating the Earth's geodynamo, as we'll see later on. As we go into the mantle, we now lose much of the iron. We're down to about 6% iron, and we see the appearance of aluminum, a little bit of aluminum. Most of the mantle is oxygen, magnesium, and silicon, with a little tasting of calcium here. As we go to the crust, again, oxygen and silicon are dominating. Magnesium, not so much now. Calcium, about the same. And then we see a little bit more aluminum, about the same amount of iron, and a wide variety of other elements. Thought question for the chapter. Imagine you're a tour guide on a journey from the Earth's surface to the center. How would you describe the material that your tour group encounters on the way down? Why is the density of material always increasing as you go down? There was a movie made back in the 50s, early 60s, I forget. Journey to the Center of the Earth. You should check it out when you're ready for a thrill. They encounter all kinds of crazy things. They start out in Iceland and they walk to the middle of the Earth where they encounter an ocean filled with dinosaurs and strange magnetic phenomena. And of course they brought a duck. Okay, so as we're going towards the center, ignoring what you might see here, you would see an increasing amount of iron, and therefore an increasing amount of iron-containing minerals until we reach the outer core, which is liquid iron. By further compressing and crunching and squeezing that liquid iron, eventually we get to a point where we see the juncture of the outer core and the inner core, which is the transition from liquid to solid. So we've made that iron, we've compressed that iron enough that it behaves as a solid instead of a liquid. The Earth system, again, is all parts of the Earth and the interactions of those parts. This includes the climate system, the plate tectonic system, the geodynamo system, and we have to consider the Earth to be an open system. It's exposed to things going on around it in space. It exchanges mass and energy with the rest of the cosmos, therefore.